So what is a vRAN? Well, the V stands for Virtualized and the RAN is Radio Access Network. So a virtualized RAN is essentially a base station where all of the processing, which we call baseband processing, is actually done in software. So a virtualized RAN means that what we can do is we can upgrade our base station very easily by reconfiguring the software, and that means that we don't have to roll out a new set of hardware at the same time. So by having a vRAN, we suddenly have a very easily reconfigurable radio network. So this is an example of the vRAN architecture that we're actually looking at in the TIP project. And there's a few key components that I'd like to identify here. So first of all, where is the baseband processing? Well, the baseband processing is the physical layer and layer 2 and 3. So what we've got on this side is the remote radio unit, and this includes the RF, so the antennas, the power amplifiers and some filters, and the lower physical layer processing. So there's a little bit of processing done at the remote radio head, or the remote radio unit. Then the rest of the baseband processing is done over here, in what we call the virtualized baseband unit. So what are the benefits of doing this? Well, one of the things is that this virtualized baseband unit can be put in a centralized location, and that can be a common compute platform. So what we can do is we can run the vBBU for several base stations in the same location, and that gives us several benefits. One of the key benefits is the pooling gain. By running all of the vBBUs in one compute location, we're doing it more efficiently. And second of all, when we want to deploy base stations in high densities, we're going to have a lot of overlapping base stations, and so there's going to be a lot of interference to manage. And by having a centralized vBBU, a lot of the coordination that needs to be done between neighbouring and overlapping base stations can be done much more effectively. So we're going to get much better interference mitigation and therefore much better capacity and overall user performance. So what is the challenge? So we're seeing all benefits as we push all of the processing into this baseband unit. The challenge is, the more of the baseband processing we push in that direction, the tougher the requirements on this front haul connection. So this is the transport link between the vBBU and the RRU. And what we're looking at in the TIP project is non-ideal transport. So we don't want a dedicated fibre here. We want to use the existing transport infrastructure that any operator might have. So that can include PON, it can include G.fast on copper, it can include DOCSIS over cable, it can be microwave links, it can be any number of links. And we want to make sure that the same vRAN solution will work for all operators regardless of the transport. So let's take a look at what this looks like in real life. So what we've got here is a virtualized function running the vBBU on this server. This server has the capacity to run many more applications, but at the moment we're just focused on the vBBU. Then the second box that we need to understand is this network emulator. So this allows us to replicate different types of transport links. So in this case, G.fast, DOCSIS, microwave or PON, and we simply enter the numbers for the throughput, latency and jitter, and this box allows us to replicate those transport networks. And then the final part of the vRAN solution is the remote radio unit. So this unit here is not a commercial product, but it's very good for prototyping, and the next things that's going to come into the lab are two different vendors producing commercially ready RRUs. But what we can see here is the antennas, and within this box we've got the power amplifiers and filters, and this little box on top is doing the small amount of processing which covers the lower physical layer. We've now set this network emulator to be ideal transport, so the transport requirements are in excess of 200 megabits per second in the downlink, and so that's sufficient to make sure that we can get maximum capacity from this single carrier remote radio unit. So as we look at the handset, we will see now, before I put my hand in the way and disturb the RF environment, we were getting about 140 megabits per second. And so that's about the peak rates that you can expect for a single carrier LTE cell. What we've done now is we've restricted the throughput going through this box, so it's going to represent quite non-ideal front haul. And what we're going to see is that this cell remains operational. Although we can't provide peak data rates, the cell can still provide a good service. So if we look at the handset now, we'll see that we're getting somewhere in the range of 30s or 40s, maybe even 50s, but that's the maximum throughput due to the fact that the transport link is restricted. So in summary, this is the vRAN solution, this is what it looks like, and one of the key aspects is the fact that it can adapt to different types of transport. When we get ideal transport, we get the best performance, but when we get more non-ideal transport, the cells remains available and we still can provide a good service. And that means that for vendors, they can produce a commercial set of products that can apply to a wide range of operators, and those operators can deploy that same set of products whatever transport they have available.